Hello class, welcome to lesson 2.2, Proving Lines Parallel. Remember that in 2.1 we actually looked at parallel lines and properties or postulates and theorems that are related to angle pairs when two parallel lines or more are cut by a transversal. This time we're going to actually prove that the lines themselves are actually parallel. So what angle relationships can be used to prove that two lines intersected by a transversal are actually parallel? So our goal is to use angle relationships to prove that these lines are parallel. And in addition, we're going to actually introduce a new way of proving things known as the flow proof. And we'll do that in one of our examples when we actually prove that two given lines are parallel. So first off, remember, we're going to go ahead and review the fact that, remember, we were dealing with parallel lines for the most part in 2.1. And the theorems and postulates that we used can only be used for parallel lines. So for example, in this case, n and m are actually parallel, and we'll indicate them with these arrows. So if they are parallel, then we know that, for example, angle 2 and angle 6 are going to be congruent. So if angle 2 were to be 30 degrees, well then angle 6 would also be 30 degrees. So what happens if they're not parallel? Well, in the case that they're not parallel, let's go ahead and just kind of dot this line, line N. We'll replace it with a dotted line, and then we'll kind of adjust it so it looks like this line, this blue line, and we'll call that new blue line, line N. And so notice that if the two angles, angles 2 and angle 6, are both 30 degrees, well then if the dotted line becomes the blue line, that no longer is the case. So now the new angle 2 is actually the new angle from the red transversal line to the new blue line is no longer 30 degrees. It's actually 25 degrees, something smaller. So because that angle is smaller, it no longer is equal to 30. And so notice that angle 2 is no longer congruent to angle 7, if we were to call angle 2 this 25 degree angle, that is. So what happens is that when you don't have parallel lines, it ruins the relationship between the angle pairs, and so they're no longer congruent, or whatever the theorem states. So in this case, remember that the angle pair postulates and theorems are not true when the lines that are cut by the transversal are not parallel. And so we indicate this in the diagram or in words in mathematical notation by using the symbol. This is the parallel symbol and then a line crossing through it. And that stands for is not parallel to. So this literally is read, line M is not parallel to line N. So if that's the case, you cannot use the postulates and theorems from 2.1. And so if the angle pair relationships are true, then we can confidently say that the lines are parallel. So you can kind of see where we're going with this. If we can show that the angle pair relationships are true, then we can truly prove that the lines are parallel. And so let's look at the corresponding angles theorem. So we know that this theorem states that if you have two parallel lines cut by a transversal and you're looking at the corresponding angles, well then that means that the two corresponding angles, in this case angle 1 and 2, are congruent. So that means that their measures are equal to each other. So that's what the theorem says from 2.1. Now if we reverse this and say that angle 1 is congruent to angle 2, then that means that the lines are parallel. Then what we just did is we reversed the logic there. We reversed the theorem, and that's called a converse. Okay, so this works in reverse as well. So when you reverse a theorem like this, it's not always going to be true. But in this case, it happens to be true. So if you reverse this theorem, called the converse, then it turns out that it's also true. So let's call this red statement P if a transversal intersects two parallel lines. And let's call this blue statement Q. So Q is corresponding angles are congruent. And so if you were to think of the corresponding angles as P leads to Q, well that means that, well, if P is true, then that means that Q is true. So if you have two parallel lines, then that means that the angles are congruent. Now if you reverse it, well now that means Q leads to P. So that means that if the corresponding angles are congruent, then that means that a transversal intersects two parallel lines. So basically saying that if the angles are the same, then you have two parallel lines. And that's known as the converse of the corresponding angles theorem. If two lines in a transversal form corresponding angles that are congruent, then that means that the lines are parallel. And so in this diagram, it says that if angle 1 is congruent to angle 2, in this case these corresponding angles, well then that means that the lines themselves, L and M, are parallel. Okay, so this is the converse of the corresponding angles theorem, and this is the theorem, one of the theorems that we will actually prove. So that's going to happen in this example. So example 1, we want to actually prove that this is true. So the way that we're going to prove this is by contradiction. So let me explain what that means. So we know that if angles 1 if angle 1 is congruent to angle 2 in this diagram, so suppose that that's true, well then that means then that M is parallel to N, right, in this diagram. So that means that the lines are parallel. So to prove this by contradiction, what we're going to do is we're going to suppose that M is not parallel to N. So we're going to say, well, this is not true. We're going to say that M is not parallel to N. And then as we pretend that that's true, if we go through our proof and find that this is not true, that they're not congruent, well then that means that there's a flaw in our assumption, and that means that it cannot be true, which means that it can't be true that they're not parallel, which means that they are parallel. So basically, if we're trying to prove the opposite and assume that it's not true, we get a flaw in our logic, well then we can reverse it and say, okay, well then it has to be true, right? So it has to be true that they're parallel. Okay, so we're going to start with that. So suppose that N and M are not parallel. So if they're not parallel, well that means that there has to be a line that is parallel. So we're going to draw another line that is parallel to M, and we'll call that line P. Okay, so suppose line P is parallel to line M. Okay. Well, in that case, that means that this angle that used to be angle 1 can be broken down into angles 3 and angle 4, right? And so we'll go ahead and label them as such. And so since line P, the blue line, is parallel to line M, because, you know, M and N are not parallel, so that means P and M have to be parallel. So since they're parallel, this means that angle 2 has to be congruent to angle 3, which is this blue angle here, by the corresponding angles theorem, right? Because now, according to this theorem, angles 3 and angles 4 are corresponding angles, so they have to be congruent by that theorem. Okay, so if they're congruent, that means that their measures are equal to each other, right? By the definition of congruent angles. So far we got that. Now we know that this red angle, angle 1, has to be equal to angle 3 plus angle 4, because these two mini angles should make up this big angle. So angle 1 is 3 plus 4, which is the angle addition postulate. Now we know that angle 2 is equal to angle 3, so by substitution we can replace this with angle 2, which we do here. And so now angle 1 is equal to angle 2 plus angle 4 by substitution property. All right, so now angle 1 is equal to angle 2, but we can see that that's a contradiction. Angle 1 is saying that angle 1 is equal to angle 2 plus some other angle. But we know that angle 1 has to be equal to angle 2, because that's what was given. Remember that the statement was if angle 1 is congruent to angle 2, then, you know, the lines are parallel. But we said that the lines are not parallel, and in doing so, we found that angle 1 is not equal to angle 2, because you have to add some other angle to 2 to get to 1. So there's no way that angle 1 equals angle 2. For example, if angle 1 were 30 degrees, and angle 2 were, and angle 4 were 5 degrees, well, then that means angle 2 would have to be 25 degrees. But by that logic, angle 2, which is 25, is not equal to angle 1, which is 30. So therefore, they're not equal. There's a contradiction there. Now, because there's a contradiction with this statement right here, this means that there's no way that line P is parallel to line M. There's no way, which means that P is not parallel to M. It means that indeed N is actually parallel to M, which is exactly what we were trying to prove. So therefore, this is the symbol for therefore, line P or line M is parallel to line M, which is what we're trying to prove. And so we go ahead and end the proof there with a box to indicate that we finished the proof. So this is a proof by contradiction. Now, if you don't understand this too much, that's okay. We're not really going to focus too much on it. The idea is that we have been able to somehow prove that two lines are parallel using this logic. Okay. So now, again, converse means you reverse the statement. Okay. So the converse of the alternate interior angles theorem states that if two lines are parallel, or if alternate interior angles are congruent, so if angle 1 in this example is congruent to angle 2, these alternate interior angles, if they're the same, then the lines indeed are parallel. Okay, so that's the converse of the alternate interior angles. Converse of the same side interior angles postulate. So if these angles add up to 180, then the lines are parallel. So that's what the converse of that is. Converse of the alternate exterior angles, if these two exterior angles are congruent, and that means the lines are parallel. Okay, so those are the converse of the theorems that we talked about in 2.1. So in 2.1, we had the regular theorems and regular postulate. 2.2, we're looking at the converse, which is the reverse of those statements. Now we're going to introduce another type of proof known as the flow proof. So flow proofs consist of arrows showing the logical connections between statements with reasons below each statement. So we'll show you how this looks like. So this is an example of a flow proof. You have a given statement and you're trying to prove something. This is your diagram. And so this right here is the start of the flow proof. So this is the actual part of the flow proof. So start with your first rectangle, your first box has your given statement. So we have that A is parallel to B, and the reason goes below each of the boxes. And the reason is that it was given. And then the arrows dictate the flow of the logic from box to box, from statement to statement. So the statements go in the box, the reasons go below the box. And so in this example, it's saying that going from this step to this step logically makes sense. Okay, so this is saying that if A is parallel to B, then angle 3 and angle 2 are a linear pair, and the reason is that that's a definition of a linear pair. And then from there you can go to the next step, which states that, well, because they're a linear pair, that means they add up to 180, and then so on. And then from this box, you also have another argument. Well, angle 1 and angle 3 are corresponding angles. And the reason is that they are corresponding angles according to the definition. And then so on. So basically the arrows dictate your logic. And if you have two things going on at once, then you have two arrows, right? But in any case, however many paths you have, they always have to lead up to the final path, which is what you're trying to prove. What you're trying to prove should be the final path. And so that is when the proof ends, whenever you reach that proven statement. So this is how a flow proof looks like. We're going to actually look at an example of a flow proof. So we're going to write a flow proof to prove the converse of the alternate interior angles theorem. So this is the alternate interior angles theorem. If angle 1 is congruent to angle 2, these are alternate interior angles, well, then that means that these lines have to be parallel. So we want to prove that. Okay, so first off, let's start with the flow proof. The given statement, which is underlined in red, goes first.
So our statement goes in the box, and the reason goes on the bottom. So the reason is that it's given. Now we're gonna do it. Now we're gonna introduce another statement. Well, this statement states that, well, angle 1, we know angle 1 is congruent to angle 3 because those two angles are vertical angles. And we know that vertical angles are congruent. And this is known as the vertical angle theorem, right? The vertical angles theorem. So that's the reason for that. You can also say that. Okay. And then we need an arrow, right? So we're going to do an arrow that goes from the given statement to the next statement. What is the next statement? Okay, so if we take these two statements together and we put them together, then we get this statement, right? So that's why we have those arrows. So if angle 1 is congruent to angle 2, and angle 1 is also congruent to angle 3, well, then that means that by the transitive property, angle 2 has to be congruent to angle 3. Okay, so remember the transitive property states that if A is equal to B, here, let's write it this way. If A equals B and B equals C, well, then that means A equals C. That's the transitive property. So in this case, B is 1, and then A is 2, and C is 3. And so this works for congruence as well. If you change this to a congruent symbol, well, then that's the transitive property of congruence. Okay, so then the next statement is that, well, once we get these two lead to that, well, then from here, then I can say, well, because angle 2 is congruent to angle 3, these are corresponding angles. It means that if they're corresponding angles and they're congruent, well, then I'm done. I can just say that these two lines are parallel by the converse of the corresponding angles theorem, and I'm done. Now, we already proved this theorem, so we can go ahead and say this. And that's the end of the proof, which we proved earlier. We proved that converse theorem earlier. Okay, so that's how you do a flow proof, for that example. Let's do another one for the converse of the same side interior angles theorem. So remember the same side interior angles. This should actually say same side interior angles postulate, I guess you can say. So we're gonna go ahead and do that. It says theorem here, but it should say postulate, I believe. So angle 1 plus angle 2 is 180. If these two add up to 180, then the lines are parallel. So let's prove it. So we have, we know that angle 1 and angle 2 is 180 because that's given. We also know that angle 1 and angle 3 add up to 180 because they're a linear pair. So these guys form a linear pair. So this is the linear pair postulate. If we put those two ideas together, then we can conclude that they're equal to each other because A equals B, B equals C, so that means A has to equal C. And so that's the transitive property, that they're equal to each other. From there, we can say, all right, we can get rid of the angle 1s by subtracting it on both sides. That leaves us with angle 2 equals angle 3. And this is known as a subtraction property because we're subtracting the same number on both sides. That leads to this result. All right, well, we have that angle 2 is equal to angle 3. So we could say that because angle 2 is equal to angle 3, well, we can say that angle 2 is congruent to angle 3. And this should be another box. This should say this is the definition of congruence, of congruent angles. And then finally, I don't have any room, so I'm going to go ahead and do this arrow to the left. Normally you would just continue in the right direction. And then finally, we say that, well, M is parallel to L because we know that these two are congruent and they're actually corresponding angles. Oh, I'm sorry, we're looking at
we're looking at these other angles here. Okay, so yeah, because angle 2 is congruent to angle 3, then that means we have to say that M is parallel to L, and that is because of the corresponding angles theorem, or the converse. Okay, so this is the converse of the corresponding angles theorem. And that concludes our proof. We proved that L is parallel to M, given that they're 180. So we finished the proof. Okay, so we're going to talk about other theorems for parallel lines. And so some of these are kind of obvious. You can prove them with other theorems. You can kind of think of them logically that way. So what happens if we have 3 parallel lines? Well, if 2 lines are parallel to the same line, then they must be parallel to each other. So for example, if A is parallel to C, for example, so if A is parallel to C and B is parallel to C, well then what does that mean about A and C? Well, that means that logically we can say that A is parallel to C, or B rather. So if A is parallel to C and B is parallel to C, then A is parallel to B. And that's sort of like a transitive property, but for parallel lines. So we're saying that if that's true, then A has to be parallel to B. So if 2 lines are parallel to the same line, they have to be parallel to each other. Another theorem states that if 2 lines are perpendicular to the same line, then they're parallel to each other. So for example, if A is perpendicular, perpendicular means it crosses at a 90-degree angle, a right angle. So A is perpendicular to C and B is perpendicular to C as well. So that means that A has to be parallel to C, or to B. And that kind of makes sense, because if you think about it, well, these 2 angles, these are corresponding angles. So if you have corresponding angles cut by a transversal, well, corresponding angles are equal. These 2 angles are equal, then that means that the lines have to be parallel by the converse of the corresponding angles theorem. So these are really 2 ways of looking at the same thing. All right, so let's finish off with an example. So here we have what looks like a barn door. And so we have a bunch of boards put together to make this door. Now, the first question states, how do you know that boards M and N are parallel? So this is board M right here, and this right here is board N. Okay, so you want to know that these 2 boards are parallel, that they're perfectly parallel, that they'll never, cross or anything like that if they were to continue forever. How do we know that? And then what should angle 1, this angle here, be in order to ensure that board B is parallel to board A? Board B, board A. Okay, so what we're going to do is, we're going to focus on part A first. How do we know that M is parallel to N? We're going to draw a diagram here. So we replace all the boards with lines, just like this. And we're going to focus on M and N. So we're going to erase everything else except for the bottom board A and M and N. Now, if you look at that, well, in this case, this is my transversal. And we want to show that these lines are parallel. That's a question mark. We don't know if they're parallel yet. However, we know that these 2 angles are both 90 degrees. And those are corresponding angles, or not corresponding angles, they're same side interior angles. Same side interior angles. And because, remember that same side interior angles add up to 180. So we know that 90 plus 90 is 180. So if the same side interior angles add up to 180, well, that means that the lines have to be parallel. That's given by the converse of the same side interior angles postulate. Another way to say it is that using the previous theorem, since both lines M and N are perpendicular to line A, then they have to be parallel, which is essentially the logic that we said earlier. So converse of the same side interior angles postulate. And so that's how we know that the boards are parallel. So what should angle 1 be sure that board B is parallel to board A? So we need to figure out angle 1. And so we're focused on B and A, and we're focused on this transversal. So let's erase everything else except for those. So we got our transversal, we got our board B and board A. Well, now we know that this angle is 35 degrees. And so if that angle is 35 degrees, well, angle 1 and angle 35, the 35 degree angle, they're same side interior angles. Same side interior angles. And so because of that, they have to add up to 180, right? Same side interior angles add up to 180. And so if these are parallel, then those add up to 180. So we have 35 plus the measure of angle 1 is equal to 180. And so we can subtract and find angle 1. So angle 1 and the 35 degree angles are same side interiors. They add up to 180. So angle 1 has to be 155. All right, guys, that's it for the video. I hope you learned something new from this lesson, and I'll see you in the next one.